I gotta set the recording.
I'm not that one.
Sorry.
Yeah, that's one.
All right, let me set the recording real quick.
Yeah. So not press play?
Good morning, everyone. All right. Hello. Order. People in the back. Okay. So we did not have any sessions yesterday afternoon, so I'm sure you are all exquisitely well rested, got plenty of sleep. But just in case you didn't, we have the perfect session for you today on flashing lights and explosions. And so to get us started, we'll have Wynn Jacobson-Vaughn.
All right. Thank you. Okay, so yeah, I'm Wynn. I'm a second-year Hubble Fellow at Caltech. And today I'll be talking about some really low Z type 2 supernova science. I know the high Z is really exciting, but there's actually quite a bit you can do at low Z for the most nearby type 2s. In terms of constraining type 2 shock power, mass loss rate, etc. So to kind of set the stage, because we're not all supernova people, I really care about massive stars, in particular in the regime that stellar evolutionary models are kind of ambiguous or unsure right now. So we need kind of empirical evidence of what happens in the last thousands of years before, say, a red supergiant explodes. And the longer you look back as the supernova shock wave traces further out into its circumstellar material, you're basically just looking back further and further in time. It's this time capsule into different stages of late stage burning. So massive stars actually are very dramatic in their cores in the last 1,000 years before explosion. And so to actually trace this, we can use a bunch of different multi-wavelength metrics to try to understand it. But today I'll kind of start with the most basic, which is the type 2 supernova light curve. So since we're not all familiar, I just wanted to break down all of the pieces of the type 2 supernova light curve with an extremely belabored analogy. So the type 2 supernova light curve is really fundamental and kind of has four main pieces. The first I won't talk about because we all argue about what actually causes a type 2 supernova to rise to peak. There's circumstellar material, there's a shocked envelope, there's so much other crazy stuff happening, so I'll just ignore that. But I have three main animals to play with here in my race of shock power, radioactive decay power, and hydrogen recombination. So the most dominant rabbit in my race right now of the type 2 supernova light curve is this hydrogen-rich rabbit. As the shocked envelope expands, it cools down. I have this immense amount of hydrogen that's recombining. It provides an immense amount of power, but this rabbit is made of hydrogen, so eventually it will recombine and die. And so I will be left with the second rabbit, which is my radioactive decay rabbit. He's very robust. I can describe his evolution extremely well. All I need is just a ball of nickel-56 synthesized in the core of my red supergiant explosion, and it's just decaying. It's producing gamma rays. They're thermalizing in my inner ejecta, and it produces this beautifully described radioactive decay powered slope. And so for the average type 2 supernova astronomer, we will stop observing kind of around here because that kind of caps out our limit of ground-based telescopes. So I'm pretty much always thinking that this radioactive decay rabbit is the best I got, and that's all that really contributes. But if you have something nearby enough or large glass telescopes, it's actually going to inverse, and this little tortoise that could is actually the dominant power source at very, very late times. And this is my shock power tortoise, or that is slowly making its way from a very non-subdominant emission mechanism into the most dominant emission mechanism at very, very late times. So what do I mean by shock power? Shock power is just all of the energy that then I convert to radiation from just the shock wave just plowing through the circumstellar material. Just the stuff that is beyond the star that the shock wave is interacting with and is just actually sapping an immense amount of energy and converting it into radiation. But compared to at early times, the supernova light is completely dominant compared to that. So it completely washes out what is happening from the forward shock and its interaction with the stuff way out. But over time, I basically get this perfect laboratory to understand shock physics, shock dynamics, shock thermalization, if I just let this radioactive decay powered source just fade away. And now I'm just left with a pure shock powered system. So what do I mean in practice? We can look at this in the multi-wavelength space, in particular in the view of a single very nearby type 2 supernova where I'm actually able to use ground-based telescopes that are not even that big to track something well beyond 500 days where this shock power emergence might actually happen. And so to kind of break down the different signatures of this shock powered emission, one of which is very smoking gun signatures in the UV. So this is a HST far UV and near UV spectrum. And if I only had radioactive decay power, I'd pretty much see no UV emission. I don't get very much at all from radioactive decay. So if I see these very beautiful emission lines of magnesium-2, Lyman alpha, that's coming from post-shock gas that's cooling down. And that tells me that I actually have this additional emission mechanism that's coming from the supernova shockwave ramming into more material, sweeping it up, and it's cooling down and producing these beautiful UV emission lines. The same thing happens in the optical, but you can actually see the transition very clearly from what is powered from nickel-56, dumping energy into the innermost ejecta. That's why my type 2 supernova looks very normal at kind of a year or so after explosion. These are very typical forbidden, semi-forbidden and permitted transitions of oxygen-1, calcium-2. This is stuff that's way deep inside the ejecta of my supernova, and I'm finally seeing it because it's becoming optically thin. And these lines are powered almost exclusively by nickel-56, just dumping their gamma rays and it's thermalizing in the innermost ejecta. But then you saw that that power source drops away. So then there's literally a morphology transition where this is radioactive decay power dominated, this is shock power dominated, all those nickel powered lines drop away, and then I'm now seeing emission only from the shock powered region. And so that's a completely different line morphology. These are boxy profiles. This comes from the post-shock gas, and so I'll talk about what that actually looks like in principle in a second. And then the last thing is just the X-ray power. The X-ray power is generated at the shock front. You can either have X-rays at the forward shock or the reverse shock. The reverse shock, which I'll show in a second, is actually the most significant because it's radiative. It actually dumps power that gets reprocessed and turns into this beautiful UV emission optical to near IR. The forward shock, though, is tracing what it actually is interacting with in the post-shock gas, the pre-shock gas right ahead of the shock. And so that actually tells me what is the evolution of the mass loss rate or the CSM density beyond my shock. So to kind of complete the picture, we wanted to take this very nearby event and create what is one of the largest spectral energy distributions of a type 2 to date, and go about 8 orders of magnitude in frequency space and map all of the different emission mechanisms to try to constrain what I'm interested in, which is the shock power budget. How much shock powered emission is actually in a type 2, and what can it tell us about shock dynamics, mass loss rate, all those things. The synchrotron emission comes from the particle acceleration at the forward shock. That's non-thermal. I'm less interested in that because it's not doing much for my optical through UV, but you can see this is the 30 micron to 0.1 micron spectrum. This is all JWST. This is all basically dust emission plus some line emission. That's really incredible. Then you have the optical spectra that I talked about earlier. This is not totally shock power dominated yet, but there's kind of a mix of both. So you have a little bit of radioactive decay and some shock power emission, and then you have the UV emission here. And then this is the X-ray spectrum at a bunch of different phases. And then this is kind of mostly driven by the forward shock because I think that most of the reverse shock power is getting dumped and thermalizes into this. But let's talk about what that actually looks like in practice. So the physical picture here is kind of this onion structure. You have gas outside of your forward shock, that's pre-shock. That's stuff that is just the wind of the red supergiant. It's not yet shocked, but eventually it's gonna get kind of swept up by the forward shock. It's gonna get put into this region between two shock. And this is the contact discontinuity. This is the cold, dense shell. This is a mixture of everything that's getting swept up continuously from ahead of the forward shock. And then it's also stuff that's getting mixed behind the reverse shock, which is the innermost ejecta. So you have this kind of dense, cool shell. It's maybe a perfect place to make dust. It's definitely a very beautiful place to reprocess radiation from your X-rays that are coming from this radiative reverse shock. Your forward shock is producing X-ray emission, but it just can't cool fast enough compared to its expansion timescale, so it's not doing much for me in terms of powering the rest of my supernova. But the reverse shock is doing all the work. It's dumping energy forward and backwards in mass coordinates, and it's powering the innermost ejecta and the stuff that's in my dense shell. And so if I really wanted to constrain what is the entire shock power budget of my supernova, I would just take my X-ray emission, how much it's been thermalized, and then subtract off the radioactive decay power, which I can constrain very well from my second rabbit in my light curve, and then I can get a pure shock power budget. How much shock power do I have to work with for my type 2? And so we did this for 23XF, and then we tried to understand what is the complete model spectrum from 0.1 to 1 microns, and how can we model it best with radiative transfer simulations. So this is kind of the first wave of ever attempting to make a non-LT model spectrum for a type 2 supernova that self-consistently goes from the far UV all the way to the mid-infrared and has all the three things that I care about: radioactive decay, shock power emission, as well as dust. Because dust is pretty essential here because it actually is very visible in the mid-infrared spectrum. This is the silicate bump. These are CO features. So there's definitely a lot of dust formation somewhere in the supernova, and so we need to care about it as well. What I think is really cool about the dust is, JWST has been devoted a lot to dust for type 2s in its first 4 cycles. This is a clear evidence that shock power is the heating mechanism for dust. Like, you have to have continuous interaction because the nickel 56 falls away. You have no other emission mechanism. So if you want to see dusty type 2s across the universe, you have to have shock power. So you have to understand shock power. And you basically get for free the fact that you can go from UV all the way to mid-infrared and understand the thermalization, like across the reprocessing across the whole spectrum. So I think that's just really cool. It's like maybe already understood, but I think this really confirms it. And so yeah, there's this kind of very nice dust continuum. And if you take the X-rays and you trace their the density that they probe as a function of radius, we're really tracing a pretty large mass loss rate for this red supergiant. This is just still for 23XF, 10 to the minus 4 solar masses per year, out to almost 1,000 years before explosion. The average red supergiant that we find in the field has a mass loss rate of 10 to the minus 6 or less. In fact, they're even smaller than we think. So this is one of the more extreme red supergiants that we've ever confirmed in its carbon burning phase. The red supergiants that we're observing, like Betelgeuse, are not there yet, but is it telling us that red supergiants do something pretty insane in their last 1,000 years before explosion? Maybe, or there's just really extreme red supergiants out there that we haven't actually identified in the Milky Way or nearby. So to kind of conclude here and look kind of more at a larger scope of type 2s, we've had HSC programs and other programs to search for this late time shock power flattening in a bunch of type 2s in the UV. We found it in some, we found it not in others. So why are some shock power powered at late times and others are not? Why do some show this boxy profiles from ongoing CSM interaction and flattening of the light curves while others just fade away into nothing? Shouldn't all my type 2 supernovae be powered by shock, CSM interaction at late times if I can prove it in one event or many events, since that is the emission mechanism that I expect? Why are some detected, why are some not? So that's kind of that's a question that we can bring into the LSST era, where we want to understand type 2s as a function of I guess their late time light curves, and see if any of these open questions can kind of be answered, and if any of these might actually contribute to the reason why we're missing some type 2s, or type 2s actually fade away faster or don't fade away. There's a lot of questions that we can answer with just larger glass telescopes, longer term monitoring, to try to decouple this whole SED. So I'll just leave here and just say that the future for old type 2 supernovae, very bright, but it needs to be a multi-wavelength effort. You need to go from near infrared, mid infrared. You need to get long-term monitoring with LSST. You need UV. You need X-rays to continually get the X-ray signature at late times. And then you can build up this kind of mass loss history, this look back time for a bunch of type 2s, and really understand if the populations of red supergiants in the local universe in their final 1,000 days, in their final 10,000 days, are really different than the type 2 supernovae across the universe or red supergiants just in general. So yeah, with that, I'll leave it. Thanks.
Shocking results. Any questions?
Super cool talk, Lynn. I'm curious if shock power is the driving force behind the dust emission. To what extent are you able to characterize the dust processing that's happening in shocks? Because that's something that we're really interested in.
Yeah.
For some of the higher studies, we want to understand the types of gradients that are going to survive this and make it into the
Sure. No, that's a fantastic question. So I didn't go into this liking dust or wanting to work on dust, but it just kind of happened. But like, from what I can understand, it's now a fundamental picture here, fundamental piece of the picture here. So I think that we kind of understand that the dust is formed in two main locations. One is beneath the forward shock in the innermost ejecta. Type 2s should always do that. Then there's this other region where it's actually being formed just by the fact that the dense shell is dense enough, the cold dense shell, because it swept up enough material that actually you can start forming these like silicate grains. But I think it's a mix of both. And I think that you really are forming the dust. I don't think that there's much survival of the pre-existing grains past the shock. I don't know enough about this, but I don't think that you're really able to preserve the structure of pre-existing dust as it passes through the shock front. I think that's really hard to do. I think that the forward shock will basically break it up and destroy it. Super high energy, I don't know. So I think that it's all formed in situ with once the dense shell is in equilibrium and it's forming there. And I think that it's a mixture of silicate and carbonaceous grains, yeah.
We'll have to move on for now, but let's continue this over coffee. Well, after the next.
Okay.
Circle back to this.
All right. Oh, you're already like that? Sorry.
All right, I don't know how Keynote works, so you'll have to start it.
I don't know how this mouse works. Okay, cool. All right. Hi, my name is Jillian Arsinajad. It's been a pleasure to get to know some of you over the course of the symposium. Thanks to the organizers for having us. The title of my talk is here, but I was talking to some people at breakfast yesterday about if you had to condense your title into one word, what would it be? And so mine, which I'm kind of proud of, was just jets, question mark. So if you take anything away from this, it's just jets, question mark. So because this is my first symposium, I did just want to talk about some of the other things that I work on, but I don't have time to talk about right now. So one of these is thinking about kilonovae, which are the thermal counterparts to neutron star mergers. And so I'm interested in how observations of these kilonovae can connect to the progenitors and remnants of these really exciting and interesting events. I'm also interested in understanding what are the best strategies on the electromagnetic end to find the next counterpart to a gravitational wave neutron star merger. Although, of course, one thing we're dealing with right now is just lower rates, so that's not something we can do anything about right now. I'm also interested in understanding what are the sites of R-process nucleosynthesis. So indirect observational evidence is sort of favoring a site that's more closely tied to recent star formation than neutron star mergers tend to be. And so I think it's a really exciting question, broad not just for us, but also for all humans who wonder where we come from, how these elements entered our universe. And then finally, what I'll be talking about today is the question, what drives fast X-ray transients? So first of all, what are fast X-ray transients? I had to ask myself this question 8 months ago. But these are sort of I like to call them the lower energy cousins of gamma ray bursts, which we've known about for many decades and have pretty well studied. Some nomenclature, you might have heard of these called X-ray flashes in the mid-2000s, and this sort of fast X-ray transient title encompasses both of those. So because I call them the cousins of gamma ray bursts, what are gamma ray bursts? So we've been detecting these high energy gamma ray flashes across the sky since the 1960s. We now have a pretty good idea that many of these come from either the mergers of neutron stars or the core collapse of a select type of ultra-stripped massive star. But on the fast X-ray transient end, we think not only these neutron star mergers and stellar core collapse could be producing these fast X-ray transient signals, but also potentially tidal disruption events, as well as stellar flares. And so while GRBs had missions to study them for a very long time, dedicated wide field missions to be observing the gamma ray sky, the X-ray sky has not had a big wide field monitor to discover these for quite a long time. And so in my talk, I'll be focusing on understanding what's driving those that come from stellar core collapse, how the fast X-ray transient is actually created, and what that tells us about the progenitor star. Okay, so again, using the analogy of GRBs, in GRBs, we have a pretty nice picture where you have a star that lost its hydrogen and helium envelope, likely through interactions with a binary companion. That binary companion has also spun it up, and so that gives this rapidly rotating, ultra-strip massive star the ability to launch a successful jet upon core collapse that is successfully able to punch through that stellar envelope and come out of the, oh, it's off. Oh, sorry. Now it's on. Okay. On the fast X-ray transient end, thank you. Okay. On the fast X-ray transient end, we think that potentially a source of these fast X-ray transients is that the jet is weak to begin with or potentially choked by this envelope. And so we're seeing this jet sort of shock that medium, and then we don't get the successful GRB that comes out, but we get some sort of X-ray emission that's short-lived. Another idea is that this could be the shock breaking out, and a signature that this might be happening is that instead of just having that core there, you actually see some helium. You have some helium in the massive star. And so what I'm interested in doing is doing follow-up of the supernovae that accompany these to test these different mechanisms. And so just a little bit of nomenclature for people that don't think about supernovae all the time. Supernova 1CBL, 1C, you don't have any hydrogen or helium in the optical, and the broad lines let you know that there's relativistic ejecta. So in the scenario where you have a 1CBL, it's sort of hard to disentangle if the FXT is coming from trapped jets or if it's coming from shock breakout. But in the instance where you have a 1B, where you do see optical helium lines, this is telling you that it's really unlikely that you're actually having a trapped jet. We don't think that you would get any emission from this mechanism based on simulations. And so this is telling you that this is more likely to be shock breakout of the star. And so I mentioned that we have small field of view X-ray telescopes. And so there's this really amazing serendipitous discovery back in 2008. They were actually observing this other supernova in the X-rays when they also detected this really bright X-ray flash, a star exploding sort of in real time in the X-rays with the Swift telescope. And so really interestingly, this supernova was a 1B, so it had an FXT, but it had strong optical helium lines. And so this led to the conclusion that this was the shock breakout people were looking for. And then also in 2008, based on the detection of this one event, it was predicted that the rate of FXTs from shock breakout would be about an order of magnitude greater than the GRB rate. So if we built a telescope to find these things, you would see them pretty often. Okay, so now we are in the era of the Einstein probe. What is the Einstein probe? You might not have heard much about it. It's a mission that was launched by the Chinese Space Agency. And so this will be my plug for access, because since it's a Chinese mission, we don't have access to the X-ray data. We just get the alerts. So if we have something like access, we can do a lot more science in the area of fast X-ray transients, because we'll have access to the data. But anyways, we get the alerts, so we can do stuff with it. Okay, and so sorry this is so low res, but I'm going to be talking now about the most nearby supernova following a fast X-ray transient. And so I guess in contrast to the events Wynn was talking about, these are pretty rare. And so this most nearby event in the last year and a half of Einstein probe is still at redshift 0.17. So we can get pretty good data on this event, but not like the beautiful data that you can get in the nearby universe. Oh, and then I worked with a wonderful team on my paper on this event. Okay, so this event was a 1CBL, so we see these really broad iron and silicon lines. We aren't seeing the helium that we were hoping could be like a smoking gun signature of shock breakout or trapped jets. But we do have some really interesting features that are popping out now that we get a good look at it. And so one of them is broadened H-alpha at about 42.5 days. This is typically seen as evidence for interaction with hydrogen, but really interestingly, it disappears fairly quickly. We do see this in a few other transients, like 2018 COW, a fast blue optical transient, but it's not something we see in comparable spectra of GRB supernovae. And so one of the potential explanations is that this is maybe interaction with a binary companion, but this is probably temporally unlikely. Another explanation is that maybe there's clumps of hydrogen-rich material that are left over from earlier common envelope phases. And this is more plausible explanation for this broadened hydrogen that we see. We also had a JWST spectrum around peak of this event. You can see some features over here, but what's really interesting is over here at 4 to 4.5 microns, we have this really broad feature that we haven't seen before in these supernovae. Dust is really hard to explain in this system. Potentially, our process elements. So if you fit this as a black body, you really get an unphysical velocity, so we also disfavor this explanation. And so right now, we're thinking maybe this is nebular iron lines. You go to the infrared, maybe that's more possible, but this could be cool to explore further. We do see, now that we have this really nice infrared feature, that there is some helium in the spectrum of this event. But based on the fact that we don't see it in the optical, we have an upper limit of about half a solar mass of helium. Oh, okay. So this is not super surprising, given that when we take infrared spectra of 1 CBLs, we do sometimes see this. But the fact that they're still lacking strong optical helium still makes it hard to distinguish between the two different scenarios. So this has not been the only FXT supernovae so far. So within the universe where we can actually probe these, we have about 3. All of these have had 1 CBLs, which you can see in contrast to that one from 2008 here, really lack helium. They also, in terms of their light curves, look a lot like 1 CBLs. They sort of live up here. And so this is leaving us with a lot of open questions, which is great to be in. And so I can leave those up there. I have no idea what time I am. Okay, cool. All right, thank you.
Great talk. We do have plenty of time for questions.
Ask about anything.
So how do you know which one of these FXTs are produced by supernova and which ones are not? Like going to X-ray meetings in the past years, like all I've heard was that this is from stellar flares and that kind of stuff.
Yeah, so most of what we know is we don't know promptly. So in general, I think those that come from TDEs tend to be longer lasting. So that could be a signature. There are some FXTs from TDEs that last for sort of day time scales. But a lot of it is just from optical follow-up. So for instance, you can find a stellar flare that corresponds to the X-ray transient and confirm that pretty quickly. Really interestingly, like earlier this year, there was a counterpart that there's no supernova found for, and we don't think it's coming from a tidal disruption event either. So that might be a merger case. But we really need to be within the volume of the universe that we can probe a supernova especially, and that puts a limit of about 0.4 redshift. And we, again, only have like 4 events at that redshift range right now.
Great. For 25 kg, did Swift also slew, and then there's like some gamma ray limits as well? Like did they?
We have Fermi limits. Getting Fermi and Einstein probe to look at the same patch of the sky is hard, so I don't know. I don't think the gamma ray limits cover the onset of the fast X-ray transient, but it did cover it for part of it, and there was no gamma ray emission.
Has there any been like at the relatively soon, like at the almost the same time for any of these yet, where the Fermi has gotten FXT like the same time as Einstein?
There's been coincident ones. I don't know about the temporal spacing, but the 4 that we have are within our local universe don't have any GRB counterparts.
All right. Well, let's thank Jillian again for a great talk.
that was my fault.
Right. All right.
Yeah, there it
Great.
goes.
So next we will hear from Lindsay about exploding white dwarfs.
Yeah. Okay, so I'm Lindsay. I'm a first-year Hubble Fellow at Northwestern, and I get to tell you about what we're learning about how white dwarfs explode with JWST. So this is the big question we're trying to answer. How do these things explode? And this is kind of a problem because these are our cosmic distance indicators, and we really don't know what's happening astrophysically with them. So kind of the two big questions we're trying to solve are, what is the system like before it explodes? What's the progenitor system? This is the single degenerate scenario, an animation where a white dwarf accretes material off of some normal non-degenerate companion star. But we know that this actually cannot explain most of what we see. And so another really promising avenue is to actually have two white dwarfs that are merging. They can either physically merge or just get close enough to tidally disrupt each other, and one or both of them can explode. This is still a very open question, and the other part of this is once we get it to explode, how does that explosion proceed? It can be fast burning, slow burning, it could be slow triggered to fast burning. We really don't know. So I want to walk you through a couple of the main mechanisms for how these white dwarfs might explode. There's theory says, you could have maybe a dozen different ways these things explode, but people first started with this detonation. So if you take a Chandrasekhar mass white dwarf and you burn it really quickly, that's called detonation. So detonations, it's like happens instantaneously. And in this case, the densities of the white dwarf stay too high, and so the highest densities will fuse to the highest mass elements like nickel, cobalt, iron. And so you actually end up getting way too much nickel. These things are brighter than we actually observe. But a key observable that we're looking for this type of explosion is seeing layering in the ejecta, because the explosion happens so fast that everything is just it burns at the density it's at, and the layers don't mix. All right, so this doesn't quite work for most 1As. So going the opposite direction, let's take a Chandrasekhar mass white dwarf and deflagrate it. Deflagration is slow burning. The star actually has time to react to the energy that's being input, and those layers start to turbulently convect, and they mix around. The problem with this is that now you puff up the star to too high of densities and you don't make enough nickel. So this slow burning with the well-mixed ejecta signatures doesn't explain most normal 1As. They actually are a good candidate for some faint types of peculiar white dwarfs. So people got clever and said, all right, let's do something in between, where we've got a little bit of slow burning to start things out, a little bit of deflagration to puff up the star just enough such that you can transition to a detonation, which is that fast burning that burns the rest of the star. Now, the observational signature that we're looking for here is to have a layered ejecta, because most of the star detonates, but there was some deflagration phase. And so we're looking for a distinction between regions in the ejecta that come from detonation or fast burning ashes versus deflagration or slow burning ashes. All right, so just briefly, I'll flash up here that there are some other fun ways things can explode. You can get a violent white dwarf merger. It is what it sounds like, a very asymmetric scenario. You can also get sub-Chandrasekhar mass white dwarfs to explode if you have a thin helium shell on the outside that ignites and then sends a shockwave and causes the rest of that carbon-oxygen core to explode. And in this case, it's a detonation, fast-burning, layered ejecta, and an observational signature might be to see an outer layer of helium-burning ashes, like an outer layer of calcium. Okay, so we actually think that maybe all of these mechanisms could come into play. We see a really big diversity of exploding white dwarfs. The normal 1As live on this black line. There are all these gray crosses. And if we actually plotted all of them, they would totally overwhelm the plot. So the normal 1As that we use for cosmology live here. But there's all sorts of peculiar events that live in other parts of phase space, which is brightness and decline rate, basically how fast the supernova fades away. And so the big picture research question that I want to answer in my fellowship here is which of these different progenitor and explosion channels can lead to these different subclasses? Maybe multiple of these mechanisms even could contribute to the same subclass. All right, so the tool that I have been using to investigate this is called nebular spectroscopy. Supernovae start very hot and dense, and this is what we call the photospheric phase. The photons can't diffuse out yet. It's too hot, too dense. You only see the outer layers. But over time, the supernova is expanding. So those layers dilute, and they start to become see-through. And so about 100 days past maximum light, you get to what's called the nebular phase. And that's when all of the ejecta is see-through. You can see all the way to the interior and actually probe what happened in the center of the star. And so this is great because those nebular spectra then give us like direct fingerprints of the composition, kinematics, and geometry of the ejecta. This is fantastic in principle. It's hard in practice, at least in the optical and the near infrared. So thermonuclear supernovae in the optical are overwhelmingly dominated by iron emission lines. And you can see from all these different spiked lines, that's where those iron lines sit in relation to one another. Supernovae have ejective velocities of 5 to 10,000 kilometers per second, so these lines broaden a lot. And that makes all of these really nearby lines blend together. So it's very difficult to extract what is the shape of one individual line. Awesomely, JWST is giving us a solution to this. So physically, the lines are much more spread out in the mid-infrared. You get line complexes that are now only a blend of 3 things, or some that are completely isolated. Additionally, we get a whole lot of other ionization states from things like cobalt and nickel, whereas the optical is mostly only iron. But the most important, I think, is that it gives us access to intermediate mass elements like argon, sulfur, calcium. And the intermediate mass elements, that's important because those are lower mass. They were nucleosynthesized at lower densities. So depending on where they're distributed in your ejecta, it can really distinguish between explosion mechanisms. So I've done studies of some other objects around the thermonuclear zoo, but the one I want to tell you about today is our most recent results on a normal type 1A, supernova 24GY. It's very nearby. We got it with JWST, the medium resolution modes, so like MIRI MRS, and we're seeing some things we've never seen before, which is exciting. But first I want to give you a little primer for why these nebular emission lines can teach us about how the geometry of the ejecta is set up. So this is my little cartoon. We're going to first start with a uniform distribution. It's spherical, so imagine this is 3D, and this is your observer along your line of sight, and we're going to do kind of a CAT scan of the ejecta. So what happens is that if you take slices along your sphere, then at each slice you get a cross-sectional area. For a sphere, your cross-section is a circle. So that's pretty simple. Now the flux that you see is at a given velocity slice is proportional to the area of your cross-section. For a circle, that's very simple. It's pi r squared. R squared gives you a parabola. So if you see a line profile that looks like a parabola, you can infer that you've got a uniform spherical distribution of material. All right, let's go one step farther in complication. Let's imagine that you take a chunk straight out of the middle. So it's still spherical. You've got a shell, a thick shell of material. And in this case, what it does to your line profile is it actually subtracts off a smaller parabola. And so you end up with a flat topped profile. You've removed emission from the center, and this flattens. Okay, so do we actually see this in real supernovae? Yes, but not quite as simplified as these uniform cases. This is a cobalt-3 line at 12 microns, and you can see it has a very close to Gaussian shape. The way that we get a Gaussian shape is actually with a Gaussian distribution, because at each cross section you've got a Gaussian, and then when you integrate that Gaussian cross section, integrating a Gaussian gives you a Gaussian. So that's very nice. This is important because it tells us actually where the radioactive iron group elements are located in the ejecta. So at these late times when it's fully nebular, all of the radioactive nickel has decayed away. It has a half-life of 6 days, and so that's gone. And now the cobalt-56 daughter product is what's continuing to power the ejecta. Okay, so we've got radioactive iron group elements roughly Gaussian distributed. Now let's look at these really nice argon line at 9 microns. This is very flat-topped. That's a really different shape. And so that tells us we've got some thick shell, but it's a little bit non-uniform. The shape of these wings, which we can actually tell in detail thanks to the MRS resolution, tells us that the material is distributed a little bit more concentrated toward that inner edge of the ring. Okay, so argon is tracing where our intermediate mass elements are located in the ejecta, and these were fused at lower densities. Okay, the coolest new thing that we observed in this supernova that we had never ever seen before is a spike of nickel right in the core, right at the center. That's a 0 velocity. But the mid-infrared also tells us that we've got a broader base of material as well. So what we can infer geometrically here is that we have some amount of material that's still located further out and a really enhanced amount of material in the core. In order to get this ratio of like a prominent spike there in the center from such a small volume, you really need a large enhancement. Now these nickel lines, like I told you, all the radioactive nickel is gone. So this is stable nickel, nickel 58, and those 2 extra neutrons are actually really important. You need, to get that additional electron capture, you need really the highest densities. Okay, so we've got a lot of high density burning, and so that tells us that we really need a near Chandrasekhar mass white dwarf. It's very hard to explain how with a sub-Chandrasekhar mass you would get densities high enough to get this much nickel. And then there's also another nickel line that shows something fun we haven't seen before, and that is that the slope of the line changes. I'm calling this like a broken slope, and you can really see that in the derivative, where it goes from a shallower slope to a steeper one. And this is kind of the geometry you get from this. So there's a little more material further out in this higher ionization state. All right, so putting this all together, we've got stable iron group elements that are located very distinctly from how the radioactive iron group elements are distributed, and even more distinctly are how the intermediate mass elements are distributed. This tells us we have a very layered ejecta, which means the explosion happened very fast, but there's actually a lot of different flavors of detonations, and so in this particular case, we can now do a little bit better and say which type of detonation we think it is directly from the data. So this line profile and this change in the slope, this break in the slope, is a signature of deflagration to detonation transition, where you have slow to fast burning. And that tells us that we are seeing distinct separated regions between the deflagration and detonation ash for the very first time. So we don't see this signature in the other types of models. Finally, we think that this is telling us that some normal 1A arise from near Chandrasekhar mass white dwarfs exploding as delayed detonations, the slow to fast burning, but we really need to probe a larger sample to see if this can explain all of the normal 1As. And finally, I will end by saying that we need more JWST observations. We have collected quite a sample across this thermonuclear zoo, but we really only have like one of most types of objects, and even the normal 1As, we have more of them, but not all in this medium resolution mode where we can do this really detailed analysis. The mid-infrared is super important for this kind of science because it gives us isolated lines from low mass elements, intermediate mass elements, radioactive ion group elements, stable ion group elements of a variety of different ionization states. And honestly, that's the best that we could ask for. So yes, I think we really need more of these medium resolution observations so we can do this very detailed analysis and be really differentiating between these different explosion mechanisms. And I'll just end by saying that JWST spectroscopy is making a really big difference in white dwarf supernova astrophysics. Every new spectrum that we're getting is showing us something new that we didn't see before. And so I think this is really reinvigorating the field of trying to understand type 1A astrophysics. Thank you.
All right, so we do not have time for questions, but I know I'll track you down later.
Okay.
Next, we will have Jason, who I suspect has not once had to explain his research to border protection.
Good.
Sorry, grab this one.
Can you guys hear me? Is this coming through? Alrighty, yeah, thanks for that introduction. I'm super happy to be here to tell you about the most energetic transients we know so far, what we think powers them, and with that, how we can use them to probe the most massive black holes in the universe. But first, I'd like to give a bit of an introduction on what are tidal disturbances, or TDEs, and that's basically when an unlikely star like this one gets a little bit too close to a black hole, the tidal forces start to stretch it apart, and eventually those tidal forces overwhelm the self-gravity of the star and it gets fully ripped apart. Some of that material eventually falls onto the black hole, powers a flare that we might be able to see, and the rest of the material is kind of thrown out into space near the black hole. And so it's nearly 40 years now that we've been trying to understand what these events are, at least initially theoretically with Martin Rees kind of doing this analytical calculation of what might the orbits look like immediately following that. And you can basically take that and get an idea of a few key characteristics of what these events would look like. And in particular, there's a few key things. One is that for typical million solar mass black holes or so, you would expect that the peak accretion rate onto the black hole is highly in excess of the Eddington limit, right? So typically we think of the Eddington limit as, you can't feed a black hole more than that. But in these cases, at least for a few months or so, weeks to months, depending on the black hole mass, you're dumping a ton of material onto the black hole. The other is that you kind of have this characteristic T to the minus 5/3 power law decline that comes from basically, the fallback of material into the black hole given this energy spread. And a little bit after that, we had some ideas about if you actually had an event like this, what would it look like in observations, right? These aren't just material falling on the black holes. We might expect to see these. And the basic picture is that these are fundamentally high energy events. Kind of the initial predictions were that they would be X-ray dominated because you have this disk of material falling into the black hole, material very close to the black hole that gets heated up to 10 to the 6 Kelvin or something like that. But you might imagine there's other ways to have some reprocessing material or whatever that allows you to get slightly lower energy photons, or even just, of course, like the tail of a black body here. So high energy sources. Perhaps the biggest surprise in the field of TDs is that most of the ones that we've found now are actually in the UV optical. There were a handful in the mid and late 90s that were discovered in the X-rays, but now the dominant channel and indeed the dominant rate of TDs that we have observationally is these sources in the UV optical. But they do look quite a bit like what we might expect for TDs, right? They have luminosities that are consistent with roughly Eddington limited accretion onto black holes of a few times 10 to the 6 solar masses. And they have this kind of characteristic T to the minus 5/3 power law slope that tells you it's a TD and probably not some other sort of weird behavior. And the other thing is that the UV optical tells us that it's not some strange class of rare supernovae that we hadn't seen before, right? They have hot blackbody-like emission that stays hot over many, many months, and they have very compact photospheres that actually recede over time, right? Not expanding like you would expect for, say, a supernova. And with this, we can do a lot of interesting things. One of those is basically try to use them as probes of black holes. And so here I'm showing some really nice work from Yuhan Yao and the ZTF collaboration, where this is basically the TDE rate, volumetric TDE rate, as a function of the black holes on which they occur. And so we're doing a really good job finding TDEs at lower mass black holes, and in some cases even pushing down almost to the intermediate mass black hole regime. But you'll notice that there's this very steep drop off at about a few times 10 to the 7, 10 to the 8 solar masses. And that's not, of course, because we don't have black holes here. We know that we do. But this is actually basically something that tells us that as a sample, these events are TDEs. This is the so-called Hills mass. We're basically above a certain black hole mass for a given star, in particular the low mass stars that we expect to dominate these rates. The total disruption of the star just occurs inside the event horizon. And so they do get disrupted, they're just not observable as flares. And so while that's great in telling us that we're seeing what we think we're seeing, it also means that we can't use these kind of regular TDEs to study the very massive black holes. And of course, this is an interesting question. But not all hope is lost. We know that there's this comes from actually what I was talking about earlier, the fallback on material. We get this very nice scaling between the time scale of the TDE and the black hole mass. And so in particular, if we went out and we said, okay, let's look for really long timescale TDEs, we could actually go and try to find some of these more massive black holes. And of course, that's what I'm going to tell you about today is I think we've found these. And these are extreme nuclear transients. These are the sources shown in red up here. They're extremely luminous, right? Quite a bit more luminous than the typical TDEs that sit at a few times 10 to the 44. And they're also quite a bit more long-lived. And of course, this also means that they're much more energetic when you combine these two. And so in particular, the most luminous and energetic of these are about 10 to the 53 ergs if you integrate out, which is about 100 times the kind of typical supernovae that Lindsay was just talking about, right? So these are incredibly energetic events. We also know at least from host galaxy scaling, so maybe take that with a grain of salt, especially given that these sources are at redshift 1 or so, they're living on more massive black holes than we're seeing for normal TDEs, at least at low redshift. I want to take a quick aside to just mention this other class of nuclear transients, and I don't have a nice graphic like the thermonuclear one because these are much rarer, but there's a growing zoo of nuclear transients that we've discovered from optical surveys, and one of these is ambiguous nuclear transients, or ANTs, and I'm just bringing this up to say there is this class of events that kind of shows this mix of TDE-like observables, in particular, black body-like UV optical, nice smooth flares, not the typical AGN variability that you see, but more AGN-like spectra and AGN-like power law X-ray emission. And the key point here is that, I think oftentimes people that are looking for TDEs try to throw away AGNs because they're noise, they're contaminants, but we should expect to see TDEs and AGNs, and actually, in theory, some AGN disks might even increase the TD rate in AGNs, but I think we're already seeing them. And that's important to note because some of the observables events tell us that they're probably living in an AGN host. And so here I'm just showing kind of a similar diagram to what I showed earlier, but with these extreme nuclear transients on them. And the key point is that, again, they have hot temperatures, 10,000, 15,000 Kelvin that persist for a long time, and their radii are relatively compact and shrink, right? So again, fully consistent with this idea of some form of accretion onto a black hole. When we look at their spectra, I think they're kind of just scaled up ambiguous nuclear transients. They have some of the narrow emission lines that tell you that either there's ongoing or perhaps just recent AGN activity in the host galaxy, but these very nice blue continua that persist, again, pointing towards this accretion picture. But of course, all of this is nice. We found some really cool events, but what's going on physically? So here I'm showing this kind of diagram I think that we saw a different version of yesterday with the luminosity or absolute magnitude versus the time scale of a transient that might be able to give us some insight into what's powering them. Of course, now with all sorts of time domain surveys across the electromagnetic spectrum, we're getting such a rich tapestry of physics in the time domain. But what I want to really draw your attention to, right, is that these extreme nuclear transients are living way, way up in this upper right part of the diagram, where essentially nothing else is living. And obviously, as you combine luminosity and timescale, you get energy, right? And I already mentioned the energies, but these are, kind of in their own world up here. And so this really begs the question of how do you actually get an event that's this energetic? And so perhaps the most obvious thing is to say, okay, we know supernovae are common. Maybe there's this really type of extreme supernova, but the problem is just they're far too energetic. If you want it to be radioactively powered, for the most energetic cases, you need a few hundred solar masses of nickel. So that's kind of insane, right? Maybe you say, okay, we're dumping a lot of material by shocking with a circumstellar material. Similarly, you need hundreds to thousands solar masses of CSM. Maybe you want it to be some exotic type of magnetar spin down, right? We see superluminous supernovae. Even for a maximally spinning magnetar, you need something of order of 5 solar masses, so way too massive to be a neutron star. So supernovae are ruled out. We heard about lens supernovae. Maybe you have one of these ones I just talked about with a bit more reasonable physical circumstance, but you're simply getting magnification from lensing. I think that's also ruled out because we simply don't see in the few events that we have so far any sort of foreground galaxy or cluster that would give you, the few times to 10 times magnification that you need for the most luminous of these. I mentioned a little bit about, these have some evidence for AGN and their hosts. Perhaps, right, these are the big volume to Z of 1. Maybe we're just seeing the very tail end of AGN activity. I think even these are too high amplitude for kind of the normal variability to describe it. Not to mention, right, that we're seeing these very coherent flares, which from AGNs are pretty rare. There is a way, though, for AGN to give these kind of coherent flares, in principle at least, and that's some sort of disk instability where in the right circumstances, maybe you can dump some material from the inner part of an accretion disk, you get a highly super Eddington accretion flow, and sure, that's pretty similar to TDEs, maybe that works. But I think the problem here, as I'll touch on a bit, is that we just don't know what they would look like. I think it's easy to turn the theoretical knobs and give accretion rates and timescales that are broadly similar, but do they look like this at all? And this, of course, brings me to the most likely explanation. I think the thing that I've been driving to this whole time is these high mass tidal disruption events. If you take our kind of existing knowledge and theory for TDEs and you try to match the timescales and energetics, it works out really nicely for something like a 3 to 10 solar mass star. Also, if you just simply take the energies that I've talked about and you basically say, okay, half of the star gets disrupted and leaves, half of it accretes, you assume some characteristic 10% efficiency of accretion, you end up getting ballpark, a solar mass or two of material for the most energetic event. So it's kind of all in this consistent picture. Same thing is true if you do this very naive scaling of, let's say, take the local TD rate, scale that to Z of 1 with the black hole density, and make some assumption about the IMF. Again, there's huge uncertainties there, especially in the nuclei of galaxies where we have some evidence to believe that they're top heavy. But if you kind of play that game, you get rates that are ballpark in the rates of what we have implied for these. And so I think that's really pointing us towards these high mass TDEs, which is super exciting for probing black holes. And so we only have a few events now, but where do we go from here? The most obvious thing is, of course, to try to find more of them. And I think in the Vera Rubin Observatory and in LSST, we're going to really be sensitive to many more. Just taking the ones we know now and kind of looking at the typical limiting magnitudes, we'll be able to see them out to past cosmic noon, Z of 2 to 3. The rates are highly uncertain, so I think at the most conservative, maybe it's a few per year, but I think that the big question is, are we actually complete to these kind of rare, long-lived transients that we're not particularly sensitive to in existing surveys? There's also, of course, the Roman Space Telescope that is even deeper and allows us to go much farther. And so in principle, we're visible to them, or we can detect them even farther. The real problem is that even though Roman has potentially the volume, it doesn't have the area. And so we kind of have to think about if there are ways to augment a larger area, like the High Latitude Wide Area Survey, to be sensitive to long-lived things. And then the other side is theory, whether that's taking kind of these excellent existing TD models and extending them to higher mass stars and black holes, or what I talked about, these AGN disk instabilities that give similar accretion rates and durations, but actually getting out some kind of observable predictions in terms of SEDs or spectra. And so I think the future is bright on the observational and hopefully the theoretical side. And I will put up my summary, and I'm happy to take any questions. Thanks.
You said that the rates of this very massive TDEs are very uncertain. So I'm wondering how many of these big massive stars would you expect in the last count in this
Yeah, that's a great question. You mean from the theoretical side?
Yes, on the theoretical side.
Yeah, so we did a very rough calculation, as I said, kind of doing the scaling to higher redshift and for more massive stars, and you get something like 10 to the minus 2 per gigaparsec per year at Z of 1, but that's with like a saltpeter, high mass IMF slope. And so in principle, if you have a top-heavy IMF, right, you can increase the rates by a decent amount. But I would say, we only have a few galaxies where we have any real insight into the nuclear IMFs, and whether or not that's true at Z of 1 is anyone's guess. From the observational side, we have a handful in relatively shallower surveys, and if you kind of just naively scale to the LSST volumes, it should be optimistic, I'm optimistic. But I think with these rare things, right, it really does come down to actually being good at detecting them in the surveys and identifying them. Yeah, and that's one of the hopes of TDs too. I was talking about black holes, but you're absolutely right. You can also try to use these distributions to understand the spins of black holes, what are the stars getting disrupted. Yeah.
Interesting, thanks.
All right, Swin.
It's really nice, Jason. So what are the prospects for, as I go to higher redshift, confirming that the disrupted star is lower metallicity?
That's a great question, and I think at low redshift, we don't know much about the stars that are getting disrupted. The models give you some weak constraint on the mass. I think in certain regimes, you can understand something about the star. So in particular, we see a few events that have kind of elevated nitrogen to carbon, and that tells you probably CNO processing. But I think the real issue is that we don't understand the accretion physics well enough to say, this is the material that's getting accreted. What does that lead to in terms of spectra? And right, like abundances are not line fluxes. And so it's a great question, I think, hopefully at some point. But yeah, it's early days in terms of modeling and really doing end-to-end, like this is the star, this is the spectrum, and kind of being able to go the other way.
Right. So that's it for this session, but let's continue all these discussions over the coffee break. All right, do we have any announcements from the leads, or are we good? All right.